Hello everyone. So today we will discuss the further topics from which we have left yesterday. We have proved up to this point that how a randomly oriented area in some random n direction is related to the stresses in the standard directions tau 1 1 1 2 or 2 2 something like that. And we have found the relation of t1 t2 t3. This relation we obtained, and after that we showed that uh, tau ij is equal to tau ji by the consequence of uh, conservation of angular momentum. Now we will come to the next topic and we will discuss some points related to pressure. Let us take a element, a triangular element like a wedge. Suppose this is the element, and this is given by delta x, this is given by delta y, and this is given by delta l. Just we need to show how pressure, what I can say about pressure at any given point. So suppose this is a large element, whatever I have drawn is a large element. Suppose a b c, I take the name, and it is perpendicular to AB, extends perpendicular to the screen on which I am writing. So the net amount of force, let me, okay, so no. So the net amount of force acting on the surface AB, which is extending perpendicular to the screen on which I am writing, this is given by px into delta y. If I consider uh, the force acting in y direction, then this will be 1 will also be there. Suppose the length perpendicular to the surface is 1. This will be py into delta x, and if this length is delta l, then the force applied from this surface is, suppose Pn is the pressure, and into delta l into 1. Now we have to find the relation between Px, Py and Pn. For the limiting case when delta x, delta y, all these things shrinks to a point, because whatever ABC I have drawn is not a point-wise description. It has its finite length, height and all. So we will apply the force balance on according to the description or free body diagram I have drawn, and later we will invoke the condition of point-wise description, that is delta x and delta y will tend to 0, and whatever information that I will get will be valid for the pressure inside any system at a given point. Okay, so let us try to write the balance of force. Balance of force in x direction. Okay, balance of force in x direction. What is the force acting in x direction? The component of, if let us say this angle is theta, so this angle will also be theta. From the simple geometry you can see, so this will be the direction of in which this force can be resolved. These are the two directions, perpendicular directions in the direction which in which the forces can be resolved. So what I can write, Pn into delta L into sine theta. This is in the positive direction of x. Okay, so this component, this particular component will be Pn into delta L into sine theta. This is in positive x direction, and this component will be Pn into delta L into cos theta. This will be along the direction of y, but negative direction of y. Okay. The next force in x direction is, comes with the negative sign. This sign is in the negative direction of x, so px into delta y into 1. Let us say some body force is acting in this particular element we have chosen. So let us say that body force is given by 1 by 2 into base is given by delta x into delta y into some depth 1 into density gives mass into body force per unit mass, which is acting in x direction. Only the x component of the body force we have taken is equal to mass into acceleration. So mass can be given by 1 by 2 into base into height gives area, into 1 gives volume, into density gives mass, and into the acceleration in x direction. This is total mass balance we have obtained for this element we have taken. Alright. Now from the simple geometry I can see that the value of sine theta comes out to be delta y divided by L from the geometry. So L sine theta comes out to be delta y. Let us say this is equation 1 and this is equation 2. So put equation 2 in equation 1. In equation 1, what we can get? Pn into delta L sine theta comes out to be equal to delta y. Let us say this is delta L because we have signified, given the name of delta L. Pn into delta y minus px into delta y plus 1 by 2 into delta x into delta y into rho into bx is equal to 1 by 2 into delta x delta y rho x. This is the total balance we have applied on this wedge like structure, in which we have not invoked the condition of point-wise description. In order to invoke the point-wise description and get the information about pressure, what is actually happening at a distinct point, so in that case we will have to invoke a limit of delta x comma delta y tending to 0. If I invoke this particular condition in the equation, what we can get? Pn into delta y. Let us say take common delta y, so Pn minus Px plus 1 by 2 into delta x into rho bx is equal to 1 by 2 into delta x rho into ax. Delta x is very small, this vanishes, this term vanishes, so these two terms comes out to be equal to 0, and we get Pn is equal to Px. Pn is equal to Px is obtained for condition when we do point-wise analysis. So if I have a fluid kept in a bucket, suppose I have fluid kept in a bucket, so at any point whose dimension is 0 dimension, so whatever force is acting from any direction comes out to be same. This is the consequence of the proof that we have obtained. We have taken a wedge like element and we have shown that if the structure of the wedge is vanishing to a point, in that case the pressure in the normal direction and x direction, which can be shown in pressure in x direction and y direction, pressure in n direction and pressure from y direction, all these comes out to be same. So at any point if the wedge goes and it vanishes to a point A or A prime, if the same wedge which we have defined here ABC vanishes to this point A prime, in that case we can conclude that the pressure from all different sides comes out to be same. This is the consequence of the proof. So what I can say, similarly you can apply the force balance in the y direction as well, and you can show this Py is equal to Pn. So generalized expression comes out to be generally Pn is equal to Py is equal to Px. This is something we obtain. Now coming on to a very important concept, but we will not go very deep right now because we are not in condition to explain the difference between these 2 points. But as the course progresses, when I will derive further expressions in the upcoming course, we will see this in great detail, that there is significant difference between mechanical pressure and thermodynamic pressure. So mechanical pressure and thermodynamic pressure. Mechanical pressure is average of tau 11, tau 22 and tau 33, or simply the summation of all these three, arithmetic average, so summation of all these three divided by 3. But the thermodynamic pressure is pressure satisfying equation of state. The simple equation of state we know is PV is equal to nRT, which is case valid for the ideal gases. So the equation of state for which the fluid I am taking is valid. From that equation of state we can find what is the value of pressure, and that pressure is called thermodynamic pressure. We will also discuss when thermodynamic pressure is equal to mechanical pressure, and when those two are distinct. This will also be a point of discussion. So keep this apart, because right now we are not in condition to discuss the concept in that detail, because there are some prerequisites for this particular concept. So we will discuss it later. But for now, just keep it in mind that mechanical pressure and thermodynamic pressure may not be same always. Maybe in some cases they turn out to be same. Mechanical pressure becomes equal to thermodynamic pressure, but in many situations we can find that the thermodynamic pressure is different from that of the mechanical pressure. Okay. After this, let us move to the density. Here we will discuss the concept of continuum hypothesis. So density is defined as limit of delta V tending to delta V star delta M divided by delta V. So generally we say that the density, the formula for density is mass by volume, mass divided by volume. So here also we are writing the same thing, but what mass and what volume, this is the point of concern for us in order to define the density of any fluid. Here comes the concept of continuum hypothesis. Continuum hypothesis. So continuum hypothesis suggests that the property of fluid is everywhere defined in the space there, but you know that for a fluid there may be some particular space where there is no any presence of molecule. So how can we define the property at that point? So continuum hypothesis comes with the solution of this, and it suggests that the property is defined everywhere, and for this we have to define the control volume. Suppose I will draw a graph and I will try to explain the concept of continuum hypothesis. Here if I have to represent density on y-axis and the corresponding length scale, associated with the control volume on x-axis. Okay, so suppose we take control volume. This is the control volume, and the size of control volume is of the order of the size of molecule. Suppose there may be existence of two molecules. These are let us say we are doing the analysis for water, and these two circles are the molecules of water. So there may be the chance that this control volume will remain void of these two water molecules, or there is no any water molecule present inside. In that case, what will the mass associated with this control volume? Mass will be, or if you have to find the density, rho 2 and rho 1. For this case, rho 2 becomes equal to 0 divided by the volume, and in this case 2m divided by volume. So what will happen? The density, you can see that here density is 0 and here density is some finite. So density fluctuations, you can see there is a lot of density fluctuation. Rho 1 is not equal to rho 2, and there is a discontinuity in the density. So we have to take the size of control volume or the length scale associated with the control volume in such a way that the movement of water molecules or any molecule of the liquid out or into the control volume does not significantly impact the density. Suppose we have 10 to the power 6 number of molecules, water molecules, and after that 100 molecules goes out, then the density will be 10 to the power 6 minus 100 divided by the delta V. And if initially this is the density when 100 molecules moved out, and rho 1 is the density when the molecules are 10 to the power 6. So you can see there is not significant variation of density, and rho 1 will approximately be equal to rho 2. So this particular length scale LS corresponds to some volume delta V. Delta V is the control volume of the control volume. Okay, so that particular volume at which the density fluctuation is not that significant, and that particular length scale corresponding to our control volume is kept under the continuum hypothesis. That is the control volume that we generally take in the fluid mechanics, because in fluid mechanics when we say fluid particle, it is a very important concept, that fluid particle does not constitute of just molecule. We are not concerned about the molecular level interaction. If we are saying that fluid particle, we are somehow referring to the length scale at which the density fluctuations are not very large and the properties are defined everywhere. So this is very important to understand, that if we in the explanation of various concepts related to fluid mechanics, when we say fluid particle, generally we understand, or we have that perception that fluid particle means the molecules. But in continuum hypothesis, where we use the differential equation, we do not say or consider the particle to be equal to the molecule. We consider particle to be equivalent to this control volume, which contains several fluid particles. Control volume which may contain fluid molecules of the order of 10 to the power 6 or so. I am not giving this is not the exact number, but I just, for the sake of explanation, I have taken this number. The number should be significantly larger, so that movement of fluid particle fluid molecules out of that control volume should not significantly affect the density of the control volume. Okay, so if the length scale is very small, then the fluctuations will be very large. So density fluctuations will be very large. But as soon as we will reach a point, a length scale, as soon as we reach certain length scale, after that the density fluctuations will be very small. So after this the density fluctuations will be very small. So in this region we will do our analysis of the fluid mechanics. This is the length scale associated with, and later it may go somewhere. So in this particular region, this will be the length scale of the fluid particle or the control volume that we will be taking to analyze any differential equation or so. Now, this is the basic concept of continuum hypothesis. If we'll take the length scale of the control volume of this order, then we can define the property at each and every point, and the continuum hypothesis holds. Okay. Now, moving on to a derivation called bulk modulus. This is also very basic derivation, bulk modulus. Bulk modulus K kappa. This is equal to minus delta P, or force by area, that is given by delta P divided by volumetric strain, delta V by V. Okay. So M is equal to, mass is given by density into volume, and just I want to show the relation of fractional change in density. The motivation for this derivation is fractional change in density. Fractional change in density is related to Mach number. These are some very basic concepts in fluid mechanics. We will discuss this beforehand, and then we will move into fluid statics as I discussed earlier. M is equal to rho into V. So we will take log ln M is equal to ln rho plus ln V. Now we will take the derivative. So mass is conserved, so dm is equal to 0. So d rho divided by rho plus dv divided by v. So dv by v can be written as minus d rho by rho. Okay. So delta v by v in other sense can be written as minus of delta rho by rho. So kappa can be written as minus of delta p divided by delta rho divided by rho. So delta rho divided by rho can be written as minus of delta p divided by k, or delta rho by rho can be written as minus 1 by k into delta p. Now delta p is something, change in pressure can be written as rho into u square. This is, or half into rho into u square. Half is the constant which can be used. The main important thing is rho u square. The dimension of rho u square, dimension of rho u square is equivalent to dimension of pressure. This you can check. Dimension of pressure. Okay. Why, the question may arise, why I have taken delta p to be equal to rho u square. This clarity comes from the non-dimensional analysis. If you have taken some course of transport phenomena, then if the convective term is dominant, then the pressure is non-dimensionalized by using rho into u square. Because I have not taught you the Navier-Stokes equation or any kind of momentum balance I have done. So right now I should not explain how pressure is scaled by using rho u square, but as we will progress and as I will explain the concept of non-dimensionalization and the significance of viscous term over the convective term or convective term over the viscous term. In that scenario, I would be able to explain how delta p can be correlated to rho u square, or maybe this case arises when convective term is dominant. Convective term is dominant, or the most of the momentum is transferred by the convective term is dominant. Or there may be other scenarios as well. When the viscous terms are dominant, then delta p would be non-dimensionalized by eta u by L, something like that. I exact do not remember, but eta pu, eta is the viscosity, eta into u by L. By using this, we can non-dimensionalize the pressure term. Exactly, I do not remember this, so I will erase this. But for the convective term, it is non-dimensionalized by rho into u square. Just the non-dimensionalization can give the scale of any unknown quantity, which can directly be interpreted. So if we write the equation, and if I non-dimensionalize all the terms, then the non-dimensionalization of pressure will come out to be rho u square if the significant term is convective transfer. So we will discuss it later. Maybe in the course of transport phenomena we can discuss this. In the course of fluid mechanics also we can discuss, but this is extensively part of transport phenomena course, where non-dimensionalization is major part to study. Okay, so keep that thing aside. Just put delta p to be equal to rho into u square. So delta rho divided by rho is equal to minus 1 by k into rho into u square. Now root under k by rho is sonic speed, and this is sonic speed. Sonic speed is disturbance, the speed of disturbance in a medium. Okay, speed of disturbance in any medium. Okay, so k by rho can be written as a square. Okay, so delta rho by rho can now be written as minus 1 by u square divided by a square. Okay, u square divided by a square, and u square by a square is written as Mach number square. So Mach number is velocity divided by the sonic speed, or speed divided by sonic speed. Speed divided by sonic speed. So this is the relation that I wanted to prove, that the fractional change in density is given by Mach number square. This is the relation, is proportional to, you can say, maybe some factors I have missed. So fractional change in density is scaled to Mach number square. Okay, this is one more derivation. Now coming on to the viscosity. Viscosity. Suppose I have a wall. And fluid is flowing over it. So we do assume that the flow is there, the fluid that is flowing is having some viscosity. There is no any inviscid fluid, means the property of fluid is there in which the viscosity is significant. So this will be some kind of velocity profile that we will obtain. How this velocity profile is obtained, we will discuss it later, but now this will be the velocity. Just by intuition you can see that the fluid which is attached to the surface of this particular plate will remain at rest, and the free stream velocity will be moving at its constant speed. Okay, so there will be certain threshold distance up to which the impact of this wall will be observed, and after this the velocity will be free stream velocity. Okay, after this the velocity will be free stream velocity. Just I have drawn it like this. Do not consider exact length of the vector by its magnitude, but it becomes continuous, like This is the free stream velocity, and this is the velocity which is getting impacted by the wall. The velocity at the wall comes out to be 0, and the velocity just here comes out to be the free stream velocity. Similar is the case at any point. Here also the same kind of velocity profile you will obtain. Here the velocity will be something like this. Here the velocity will be something like this, and it will get reduced. Okay, this is the correct profile. This should not be the correct profile. I will remove this. If you want to draw, you can draw like this. Now it will convey the right magnitude as well. Okay, here the velocity is 0. Here the velocity is u infinity. Here the velocity is 0.99 times u infinity. Here maybe some 0.5 times, maybe in between somewhere 0.5 times u infinity, somewhere 0.2 times u infinity, and later here 0 times u infinity. And here velocity is u infinity. Here also 0.99 times u infinity, somewhere in between 0.5 times u infinity, and similarly somewhere like 0.2 times u infinity. Some at the wall 0 times u infinity. Everywhere at the wall the velocity will be 0. So how you can see that the layer which is at the top is moving at a greater speed, but the layer which is at the bottom is moving at a lower speed. Okay, so here you can see that if the distance between these two is delta y, and this is the velocity given by velocity for the top layer is u plus delta u, and velocity for the bottom layer is u. Okay, so what I can say that after time delta t, this is the bottom plate moving at bottom layer moving at a velocity u. Okay, and the top layer is moving at a velocity delta u. So in time delta t, the bottom layer travels, suppose a distance u into delta t. Initially it was here, and finally from A it reached to B. The top layer which was at A prime, after the same time delta t, because it has a greater speed of u plus delta u, because it is at delta y above this particular AB. This is delta y above, and the velocity of any layer above is larger. So I can say that u plus delta u into delta t will be the distance traveled by the point which was originally located at A prime, now can reach B prime. So I can draw a triangle over here. And suppose this angle is theta. So this particular length I can call it is u into delta t, which is same as AB. Okay, and suppose I point this as C prime. So AB is equal to A prime C prime is equal to u into delta t. This is clear. So B prime C prime will be equal to u plus delta u into delta t minus u into delta t, which will come out to be delta u delta t. So B prime C prime will come out to be equal to delta u delta t. So if I want to find tan theta, I can write delta u delta t divided by delta y. Delta u delta t divided by delta y. Delta u delta t divided by delta y. For very small angle theta, what I can say tan theta is equal to theta. This is the mathematical consequence. Tan theta will approximately equal to theta if I assume theta to be very small. You can check in calculator by just putting the value of theta in radians. The tan theta value will approximately come out to be same whatever value of theta you will enter. So I can write for approximately tan theta is equal to delta u delta t divided by delta y. Now take delta t in denominator. So I can write this Suppose let's say this is change in angle delta theta, tan of delta theta. I will represent theta by delta theta, delta theta, delta theta, and this. So delta theta by delta t will come out to be equal to delta u by delta y, delta u by delta y. So what you can say, this is, let us take limit of delta y tends to 0. Now I am saying that the layers that we have taken are approximately close to each other, and the difference of height between the two layers AB and A prime B prime is differential, or it is tending to 0. In that case, d theta by dt will come out to be equal to du by dy. If the delta y will be very small, in that case the difference in velocity will be very small. So if I write delta y to be equal to dy, I will have to write delta u to be equal to du. Okay, and d theta in place of delta theta and dt. Okay, so the strain rate, this gamma dot will come out to be du by dy. Okay, the rate of strain comes out to be this, and we know that shear stress is proportional to strain rate, rate of strain rate. Then shear stress is proportional to gamma dot, and since gamma dot is equal to du by dy, so shear stress is proportional to du by dy. Then what I can say, we can remove the proportionality sign, and we can put the value of mu, viscosity, into du by dy. So this comes out to be the general relation of shear stress is proportional to strain rate, and the constant is called viscosity, and we obtain this relation. Mu is called coefficient of viscosity. Coefficient of viscosity. The point to be noted here is the example that I have taken. I have assumed that the flow is only taking place in x direction. Flow is only taking place in a particular x direction, and the velocity gradient is present in y direction. For that particular case, we have obtained the shear stress to be equal to mu into du by dy, or shear stress to be proportional to the velocity gradient. But this is just a basic physics that we have studied up to class 12 secondary school. Apart from this, we will have to go in further details how shear stress is related to the velocity gradient, and further in the course we will see that the shear stress is not just equal to tau. When I will introduce the concept of tensor, in that case I will say that the shear stress is not just proportional to du by dy, or it is proportional to the symmetric part of the velocity gradient tensor. The velocity gradient, suppose if I have to say velocity gradient tensor, you can write tau 1 2, where 1 indicates x and 2 indicates y, will become equal to mu into del u by del y plus del v by del x. This comes, and similarly you can write it for the other components as well. So I've not taught this tau 1 2 is, I have not taught this till the explanation that I have given, but just I want to say that whatever I have explained is not the complete information. It is just the partial information based on the previous knowledge that we had. We just tried to prove that how shear stress is related to the velocity gradient if the flow is only taking in a direction and the gradient is in y direction. Okay, but the most general form of shear stress is not this. This is a very specific case of the shear stress, how shear stress is varying and how it is related with the strain rate. Further discussion will open the gate to understand how shear stress is actually related to the strain rate. So in that case, you will study that the shear stress is proportional to not to strain rate, but to symmetric part of strain rate. This idea, from where this idea came into picture, that we will also discuss. If we rotate a body having some fluid in it with some angular velocity, and there is no any relative motion between the two layers in between, then will there be any shear stress? The answer is no. So, in order to explain all those paradox that we were generally encountering by considering that shear stress is proportional to strain rate, we had to define that total stress is not proportional to strain rate, but it's symmetric part. Okay, that is the point of discussion that we will be taking further in the course later. For now, just you try to understand how we have derived the expression tau and how it is related to du by dy. Okay. The next topic that I want to take is kinematic viscosity. Kinematic viscosity. Kinematic viscosity. Kinematic viscosity nu is defined as mu divided by rho. Mu is the viscosity and rho is the density. So what the unit of viscosity comes out to be kg per meter per second divided by the unit of density is kg per meter cube. Just I forgot to do the dimensional analysis of mu, so let us do it later. And let us discuss about the unit of viscosity first. Okay, let us discuss about the unit of viscosity first. Mu is equal to tau divided by du by dy. Okay, the units of, let us say, take the dimension of tau divided by dimension of du by dy. The dimension of tau comes out to be force per unit area, because it is shear stress or stress. So force per unit area, force is kg meter per second square, so mlt minus 2, and for per unit area L to the power minus 2 divided by U is L into T to the power minus 1 and divided by the unit of Y is L. So it comes out to be m L to the power minus 1 T to the power minus 2 divided by T to the power minus 1. This comes out to be equal to m L minus 1 T minus 1. So the unit of viscosity comes out to be equal to kg per meter per second. For m, I have wrote kg. For per unit length and per unit time, I have written meter per second. Okay, and this is the SI unit, kg per meter per second, or you can say Pascal second. Pascal second is also unit, but so I have written this unit in both the forms. From the basics I have derived, it comes out to be kg per meter per second, or also you can say Pascal second, because the unit of tau can be written in terms of Pascal, and du by dy, for that you have written Pascal second. Sorry, for that you have written second. So ultimately it comes out to be Pascal second. Okay. So the unit of kinematic viscosity, kg per meter per second divided by kg per meter cube. Now this comes out to be equal to meter square per second. Now I will write the difference between the viscosity and the kinematic viscosity. Viscosity refers to carry of momentum or diffuse the disturbance in momentum to outer fluid. Okay, this refers to carry momentum or diffuse disturbance to outer fluid. Whatever example that I have shown here, because of the viscosity, the impact of the wall is seen up to some extent. If there had been no viscosity in the fluid, the velocity at this particular wall would have been same as that of the u infinity, and everywhere the velocity would have been very uniform. The presence of viscosity leads to the variation of velocity from the wall to some, up to some extent it reaches u infinity. The velocity will be zero at the wall, and gradually it increases to u infinity at some height, and that is called the boundary layer thickness, which is again a point of discussion. It will take 2 or 3 classes to explain the concept of boundary layer. So this is the basic idea. Because of the existence of viscosity only, the fluid comes the velocity of the fluid varies in the y direction. Okay, the next thing is density. Density is something which refers to maintain the momentum. Maintain the momentum. So ultimately, in the kinematic viscosity, we have a term mu in the numerator and rho in the denominator. So mu is the term which refers to the to diffuse the momentum, and density is something which leads to maintain the momentum. So viscosity is a term which gives the comparative study of how the momentum is diffused and how the momentum is maintained. So it is the relative of these two quantities, mu and rho. So if the kinematic viscosity is very high, the tendency of fluid to diffuse the momentum is greater than maintaining the momentum. But if density is dominant over the viscosity, in that case the fluid will tend to continue or maintain the momentum. So this kinematic viscosity will give the comparison between the mu and the rho. Okay, so this was all. We will stop today here and we will continue in the next class.